Good morning. We are going to begin our second unit on the mole concept. And to begin with, we are going to focus on measurement and data collection that can be made, qualitative and quantitative measurements. Qualitative measurements describe a property in general terms. For instance, saying that the sky is blue or that I'm wearing a green shirt. That is an example of a qualitative measurement. Saying that today is a hot day is qualitative. A quantitative measurement contains a number. If I said that a friend of mine in Canada said it was pretty hot today with a high temperature of 35 degrees, I would be making a quantitative measurement. However, it would lack context because you might be saying to yourself, ooh, 35 degrees? Down here in Georgia, that doesn't seem like that would be very hot. But if I put the context of 35 degrees Celsius onto that measurement, now it would make a lot more sense by attaching a specific unit to my number. So in order to be a proper quantitative measurement, I need to have not only a number, but also a unit to give it meaning. When scientists collect data, they record measurements as accurately as they possibly can, and they report the measurements taken to reflect the accuracy and the precision of the instruments that they use to collect the data. Whenever we report a measurement, we always want to ensure the accuracy of the measurements, to make sure that we tell others only what we actually know based on our equipment and its limitations. There is no device in the world that can take exact measurements. So the accuracy of a measuring device is how close a measurement comes to the actual or the true value. The precision measures how close a series of measurements are to each other. It does not matter whether they are accurate or not. We can have different types of errors that are involved in a measurement based on whether it is coming from a human error of reading the instrument or whether the instrument itself is just flawed. If we have a error that's occurring on either side of that true value, then we can call that a random error because it's just the measuring device and how we're reading it. We can also have something that we call a systemic error where the measuring device is somehow flawed and it's consistently making the measurements on one side of the true value. So meaning that it's always measuring 10 grams more than what we would expect it to be. You have three possible scenarios when you're talking about accuracy and precision. The best scenario would be A, where we have good precision and good accuracy. You can see in this example we have a dartboard where we've had darts thrown at it, and all three of the darts are found in the bullseye. So not only was the thrower's accuracy good, but also had strong precision as well. In the second example, you can see that we had poor accuracy, but we had good precision. We didn't hit the target, we didn't hit the bullseye, but all three of the darts are found in the exact same position. And then in our final example, we have poor accuracy and poor precision. So you can see in that sense here, we now have not only the thrower not hitting the target, but also being all over the place on the dartboard as well. In any experiment, we're always going to have a small degree of error that can take place. When we want to determine just how much error has taken place, we can look at the experimental value minus the accepted value and divide it again by the accepted value. The percent error, we just take the absolute value because it doesn't matter which side it comes on, but we want to see just what that percentage of the error happens to be. So you take the absolute value of the error divided by the accepted value and multiplied by 100%. For this year, we want to strive to have all of our lab experiments, when you guys come back, being less than 5% error. When making measurements in the laboratory, we need to look at the limitations of the measuring device. The significant figures are all the numbers that are actually measured accurately plus one that is an estimated value. In this example, you can see I have a block of wood that's being measured. The first measuring device that we have measures exactly 1 meter from side to side. So there are no markings on here to let us further break it down. So I can see from this that it is a little bit greater than halfway, because halfway would be somewhere roughly right around here, and it's a little bit further than halfway. So because my known value is 1 meter increments, then I have to go to the tenths place to make my estimate. Since it's a little bit more than halfway, we can say that this would represent 0.6 meters. I cannot get any more accurate than that with this measurement because I cannot break it down into smaller known values. When we look at the second example, now I have a decimeter stick instead. I still have a total length of 1 meter, but it now gives me the number of centimeters or decimeters in this device. And so now, hopefully you can see, I can go at least to the 60 centimeters or 6 decimeters, but not quite 7. So I know with a degree of accuracy that it's at least 6, and now I have to go to the hundredths place to make an estimate. And since this is closer to the 60 than it is to the 70, we're going to write it as 0.61 meters, or we could say 61 centimeters or 6.1 decimeters. In our last example, we can break it down even further. And I know it's a little bit hard to see, but in this example, we now have the same meter stick, but I now have an additional set of markings, 1 centimeter, for each one of the lines that are present here. So now when I look at this, I can see that the end of the block of wood is somewhere between the 60 and the 61 centimeters. And so we know it's at least 60, and we have to do the estimate, and it's closer to the 1 than it is to the 0, so we can estimate it with a 7. So that last digit, the 7, is an estimated digit, whereas the 1 was estimated as well in the second example. So you can see as the accuracy of my measuring device has increased, I can now report more numbers with confidence for my answer. We're now going to look at the rules for determining the number of significant figures in a measurement. Any non-zero numbers will always be significant. So in the example 1.23456, that will have 6 significant digits. The zeros are the tricky numbers that we have to assign significant figures for. Some of the zeros will be significant while others will not. The first example that we have will be zeros within a number are always significant. We call these trapped zeros. Since there are significant digits, in this case the 4 and the 8 or the 4 and the 5, with zeros in between them, both the 4 and the 8 are significant, so therefore the 0 in between will be significant as well. I just want to make a note to you guys here really quickly that it could be a 0 on the outside, and that could make it a significant digit under certain circumstances, and so any zeros in the middle between those would also be significant. The second example is that if zeros do nothing but set the decimal placement, they are not significant. So when I look at 470,000, that has 2 significant figures. 0.00000000098 also has only 2 significant digits. The first 9 zeros here only tell us where the decimal place is located. The trailing zeros, this is what I was kind of referencing a second ago. Trailing zeros that aren't needed to hold the decimal place are significant. So when I see 4.00, those extra zeros are helping to show the accuracy of our measuring device. So these zeros would be significant. So there has to be a 0 that's occurring after a number and after the decimal place in order for it to be significant. So the first example has 3. When I look at the second example, notice here again I have all these zeros out in front without a number. There is a decimal point, but there is not a non-zero number to the left of all these zeros. And so as a result, these first zeros are insignificant. However, when I look at my last 0 that's present here, now it's coming after the decimal point and after a non-zero number, so it will be significant. So this would be an example, again, of a trailing 0. The last thing, if we have exact numbers or definitions, they will have an infinite number of significant digits. So if we were to count and we saw that there were 12 people, that's not an estimate. That is an exact number. Same type of thing if I go to the store and I buy a 6-pack of Cokes. There would be exactly 6 cans of Coke, and therefore that would not be an estimated number, that would be an exact number. Now I'm going to give you a nice shortcut here that you can do to kind of get around having to memorize all these different rules. And what this comes from is thinking about the United States map. You can see here on the side we have the Atlantic Ocean and we have the Pacific Ocean. So all of this is going to be looked at in terms of the decimal point. The Atlantic side, that stands for if the decimal point is absent, and the Pacific side is if the decimal point is present. So next year when you guys take U.S. history, you're going to learn about a concept called manifest destiny, and that was the desire of the colonials to stretch the country from coast to coast. So we're going to use that principle when we're talking about our significant digits. So when we look at a number, we want to determine whether or not the decimal point is showing. So that's the first thing. We want to look for that presence of the decimal point. This is going to tell us again which side of the U.S. map to start on. If the decimal point is present, then we're going to start on the left side of the numbers, find the first non-zero number, and then we would simply count to the right, however many digits that happens to be. So as you can see in this first example, I have 0.00000005600. So as I start on my left side, I have my decimal point showing. I come down here, the 5 is my first non-zero number, so now I'm going to count all the digits going to the right of the 5. So I'd have the 5, 6, and the 2 zeros, which will give me a total of 4 significant digits. When I look at a number where the decimal point is not showing, it is absent, now I'm going to start on the right side of the number and I'm going to count all the digits to the left. So finding my first non-zero number from the right side, again I have all these zeros here, so the 6 would represent my first non-zero number. So I'm just going to count all of the digits going to the left. So in this case, 156 billion, that would have 3 significant digits. If you look at the example that I gave you here in the box, we have 40.50. So I have the decimal point showing, so I'm going to find the first non-zero number on the left, and I'm going to count all the digits going to the right. So I have 4, 0, 5, and 0. So this one with that would have 4 significant figures. This works for numbers that are less than 1 as well. As you can see, again, you just find the first non-zero number and count all of your digits going to the right. Okay, so now let's look at a few example problems for how we count our significant digits. So for each of these measurements, we want to determine the number of significant figures. So in my first measurement, the 123 meters, again, I have no zeros in my number, so every single digit would be significant. So my first one would have 3. When I go to my second one, now I have all those trapped zeros, but again, using our shortcut, Notice the decimal point is not present. So I'm going to find the first non-zero number on the right, and I'm going to count to the left. So I have 1, 2, 3, 4, 5 significant digits. When I look at my third example, 9.8000 times 10 to the fourth. Please understand, we haven't talked about scientific notation quite yet. It'll be here in a couple of minutes. But the times 10 to the fourth power, that is just showing us decimal placement. So therefore, this part is not significant. So when I focus on the coefficient, the number that's out in front, notice I have the decimal point showing. So I'm going to start with the 9, and I'm going to count to the right. So I have 1, 2, 3, 4, 5 significant digits. When I look at the fourth example, 22 meter sticks. Again, no non-zero numbers, so both of the 2's are significant. So that would be 2 significant digits. When I look at my fifth example, I have the decimal point showing. So again, find the first non-zero number on the left and count to the right. So I have 4 significant digits. And finally, 98,000 meters. I have no decimal point showing, so I'm going to start on the right, find my first non-zero number, and count to the left. So I have the 9 and the 8 for 2. All right, so now it's your turn. Take a moment and see if you can get the correct numbers. Pause the video quickly, and then we'll go over the answers. Okay, so hopefully you have gone through the answers at this point. Looking at the number of significant figures in each of these measurements, 143 grams. Again, no non-zero numbers, so that one's easy. I know I have 3 significant figures. When I look at my second example, 0.074 meters. Again, decimal point is showing, so I go from the left and I count to the right. So this one would have 2 significant digits. In my third example, I have 8.750 times 10 to the minus 2 grams. The 10 to the minus 2, that is not significant, just showing us decimal placement. So when I look at my number here, decimal point is showing, and I have a 0 on the end, so that's our trailing zeros. So I'm going to start at the 8, and I'm going to count to the right, 1, 2, 3, 4 for my significant digits. And then finally, 1.072, a trap 0 situation. Decimal point is showing. First number on the left, count to the right. So I have 1, 2, 3, 4 digits. Whenever we are adding or subtracting a set of numbers, the answer will always be rounded to the number of decimal places in the quantity with the smallest number of decimal places. So as I look at this example here, essentially what we're saying is that whichever number is the least accurate measurement, our answer is going to be limited to that least accurate measurement. So when I look at 1.23, hopefully you can see that the 1.23 goes to the 100th place, whereas the 4.567 goes to the thousandths place. If I were to add those two numbers together, unrounded, I would have 5.797 as my answer. So now I need to round my answer so that it will report to the hundredths place. So I can essentially just draw a line after the 9 and before the 7, and I use the 7 for rounding. Since 7 is greater than 5, we would round this number up, so our final answer would then become 5.80. So in this practice problem, it is asking you to align the decimal points and add the numbers, and then round the answers that will match the measurement with the least number of decimal places. So when we look at our numbers here, we have 12.52, again going to the hundredths place, 349.0, which will go to the tenths place, and 8.24, which goes to the hundredths place again. So the easiest thing that you can do for any of these types of problems is to literally just draw a line down after the last known value for your smallest measurement in terms of the number of decimal places, which in this case is the 349.0. So anything that is done after the tenths place is going to be used for rounding, because we literally have no idea what this number could be for the 349.0. So as I add those together, 369.76. Again, the 6 will round up, so I would have 369.8 meters. When multiplying or dividing, the number of significant figures in your answer is determined by which measurement contains the least number of significant figures. So when we look at a few of our example problems, we have 2 times 10.0. So the 2 would have just one significant figure, the 10.0, if you remember, with that number and decimal point showing to the left of the 0. Both of those zeros are significant, so I have 3 significant figures here. Since I have one significant figure for the 2 versus 3 for the 10.0, my answer 20 must be rounded so that it has only one significant figure. So by having 20 without the decimal point showing, that makes that second 0 insignificant. When we look at our second example, 66 divided by 2 equals 33. Now, again, we are limited by having only one significant figure for our answer. So 66 divided by 2 would be rounded to 30 because the second 3 would round down. And by not placing the 0, again, that makes it not significant. When I look at my next example, 5.005 times 10 to the times 2.0, that is going to equal 10.01, which will be rounded to 10. But now notice the decimal point is showing, so that 0 would be significant. So I would have 2 significant figures, or I could have 1.0 times 10 to the first power. Again, the times 10 to the first power, just showing decimal placement, is not significant, but the 1.0 would be for 2 significant figures. You may have wondered, why do multiplication and division have different rules from adding and subtracting? So when we are talking about adding or subtracting two numbers, you're adding or subtracting their uncertainties. If one of the numbers is smaller than the uncertainty of the other, it doesn't make that much of a difference in the value. Thus, when we're talking about adding something that goes to the hundreds place with something that goes to the thousands place, we can be accurate in our measurement to the hundreds place. And so that last little bit that's just the thousands place is not going to impact our answer to any great degree. So it's going to be limited by the location of the digits, not the amount of significant digits that becomes important. When we talk about multiplying and dividing, you're going to be multiplying or dividing the uncertainties. So that's going to be a percentage by which you're uncertain, and the uncertainty in the number divided by the number itself. This is given roughly by the number of digits regardless of their placement in terms of the powers of 10. Hence, the number of digits is what is important. So when we're multiplying and dividing, we simply want to look at how many significant digits each number multiplied or divided has. Whereas when we're adding and subtracting, we just want to see which one is our least accurate measurement, which one limits that degree of certainty that we have. So now we're going to talk about proper rounding with significant figures. This is going to be the part that's going to be hardest for you initially to kind of wrap your brain around. We're so used to just simply plugging in a couple of numbers into our calculator and hitting the enter button and then getting an answer that has 8 to 10 different numbers after the decimal place. But you have to remember, whenever we're talking about looking at a number, that is representing a measurement that has been made in the lab. And so we are limited in those numbers to however accurate our measuring device happens to be. So when we talk about the rounding rules, remember we want to follow our Atlantic and Pacific rules that we talked about for determining significant figures. So as I look at this value here, when I start off, I have those trailing zeros. I have the decimal point showing, but I'm going to find the first non-zero number that is on the right or left and count to the right. So I would cut off after the 7. Everything here is my answer, and then I use the 8 for rounding. So I'd have 0.00568. Again, those zeros must stay, even though they're not significant. They are showing us where the decimal place is located. So I need to make sure that I include those in my answer, or I could also represent it as 5.68 times 10 to the negative third power. In our next example, I have 12,345. So again, I'm going to take three numbers and start counting those. So I have 1, 2, 3, and then 0, 0 for my answer. Again, the 4 is the first number. I can't double round, so I can't say, oh, that 5 is going to make the 4 into a 5, and then that 5 will then make the 3 into a 4. It doesn't work that way. You only use the first number to the left of whatever your cutoff happens to be, and that will determine your significant figures. So as we move forward here, I now have one last example, 12,355. So in this case, now I can cut off after that 3, and I would have 12,400 because that 5 will round up. For scientific notation, this is when we have numbers that are either really, really large or really, really small, and we're trying to make them into a more usable numbers. So that way we don't have to count all the zeros for our answer. So when we write scientific notation, it is a number that's written up as a product of two numbers, the coefficient and then 10 raised to a power. It's really simple to help you remember. When you are looking at the number, it must be written with one number to the left of the decimal and the rest to the right of the decimal. So our number must be between 1.0 and 9.9 to correctly report our answer. There are situations that we want to manipulate to make the processes of adding, subtracting, multiplying, dividing easier, and so we can manipulate what our number is in scientific notation, but always at the end we would have to go back and convert it back so our final answer is between 1.0 and 9.9, and then you would multiply that times 10 raised to some power n. The exponent will indicate how many decimal places should be moved to the right or the left. The easy thing to remember, if your number is less than 1, then your exponent will always be negative, and then if your number is greater than 1, the exponent will always be positive. So it works kind of both ways. If I have a positive exponent and I'm trying to put it back into a normal notation, since the exponent is positive, I know that's greater than 10, so I'm going to move the decimal point to the right to make the number go back to normal notation. Same thing, if I have a negative value for my exponent, then that means that my number is less than 1, and so now I'm going to move my decimal point to the left to make the number go back to normal notation. So just like significant figures, scientific notation is going to have a specific set of rules that we're going to follow when we're adding or subtracting versus multiplying and dividing. When we're adding and subtracting, we want to move the decimal point and change the exponent so that both numbers have the same exponent. Once you have made the exponents the same, you can add or subtract the coefficients out in front and then just carry over the exponent to the end. If you need to at the end, then convert back to the scientific notation to get the number between 1.0 and 9.9. So if we look at an example here, I have 4.3 times 10 to the 5th plus 6.7 times 10 to the 7th. Notice that I have a difference of 2 in my exponents. So I'm going to take my larger of my two exponents and I'm going to bring it down. So instead of saying 6.7 times 10 to the 7th, I'm now going to say 670 times 10 to the 5th. Now I have 10 to the 5th and 10 to the 5th. My exponents are the same, so I can now carry that over. And now I simply add my numbers together. Since I had 6.7 changing to 670, I can now simply add 670 plus 4.3, so I'd have 674.3 for my answer in terms of significant figures. And then I want to move that back, so I could then say, moving this 2 spots to the left, I'm making this part here a larger exponent value, so I'd end up with 6.743 times 10 to the 7th power. Okay, so next we're going to look at multiplying. When you multiply numbers together, you're going to multiply the coefficients and then you're going to add your exponents together. Sometimes we won't have to do anything because the numbers will be small enough to stay within 10, but most of the time we're going to have to move the decimal and then change the exponent until the number returns to the scientific notation. So let's look at an example using those same numbers that we started with. When I take 4.3 times 10 to the 5th and 10 times 10 to the 7th power, I can simply multiply 4.3 and 6.7. That would give me 28.8. Notice that number is larger than 10, so I'm going to have to adjust my exponents at the end for this one. I have 10 to the 5th plus 10 to the 7th, so that would now give me 10 to the 12th power. This number, if I were to rewrite this into scientific notation and just kind of break these two parts up together, I could say 2.88 times 10 to the 1st power for the 28.8, and then I can multiply that times 1 times 10 to the 12th. So 2.88 times 1, that would give me 2.88. 10 to the 1st plus 10 to the 12th would give me 10 to the 13th. So my final answer, 2.88 times 10 to the 13th power. When we are dealing with significant figures, again, I am multiplying my numbers together. It is the exponents that we would ignore because they're showing decimal placement. So 6.7 and 4.3 each would have two significant figures. So with significant figures, my answer would become 2.9 times 10 to the 13th power. For division, it's going to follow a very similar process. We're going to take the two numbers and divide them as the coefficients, like you normally would, and then we're going to subtract the exponents instead. If you need to at the end, you can then move the decimal point and change the exponent until you get the number to return to proper scientific notation. So as an example for this, if we take 8.8 times 10 to the 6th and we divide it by 2 times 10 to the 2nd, when we look at the numbers, again, 8.8 divided by 2, that's going to give me 4.4, and then I would have 10 to the 6 minus 10 to the 2, so 6 minus 2 would be the 4th power. So in this case, it's already in scientific notation properly with the 4.4. I got my number between 1.0 and 9.9, so I don't have to manipulate anything with the coefficients out in front or with the exponent for this answer. What I do want to go over though is, again, if we were doing our answer with significant figures for this, the 8.8, that has two significant figures. The 2 has one significant figure, so my answer would have to be rounded so that it had only one significant figure. So instead of having 4.4 times 10 to the 4th power with significant figures, my answer would become 4 times 10 to the 4th. Now we're going to talk about the measurements and how we report them. The SI system was created in the early 60s as a method for scientists around the world to be able to communicate with each other effectively. If every scientist used a different set of units, the communication would be different, if not impossible. So we devised a common system of units that are called the International System of Units, or the SI system. The SI system has 7 base units that are based on an object or event in the physical world. The table below lists the 7 SI base units and their abbreviations. We have more units besides just these. These are the base units. We have derived units, which will be a combination of one or more of these SI base units. We'll talk more about a couple of examples with that in just a moment. But for your 7 SI base units, we have time, which is measured in the seconds. Its symbol is an S. We have length, which is measured in meters, and that is an M. We have mass, which is measured in kilograms, and that is kg. Temperature is measured on the Kelvin scale, and it is a capital K for its symbol. The amount of substance, this is one of the most important ones for us in chemistry. The amount of substance is the mole, and it is abbreviated as MOL. Don't ask me why. Doesn't really make a whole lot of sense to just take off the E, but that's what they did. We have electric current, which is measured in amperes, and it is a capital A. And then finally we have luminous intensity, which is a candela. And just like you think about this, luminous basically meaning light, we're talking about the intensity of a light. So when we're measuring candelas, it sounds very much like a candle. So its symbol is a CD. So again, these are the base units that we have. So just an example, as I mentioned, we have derived units as well, which is a combination of one or more of these. One of the big things that we measure in a chemistry lab, which you will probably notice is lacking off of this chart, is volume. And so typically we talk about volume being measured in liters. However, when you look at this and think about it from a math perspective, I could take, to solve for volume, length times width times height. So I have 3 different lengths that I would multiply together to have it equal the volume. That's why it's a derived unit. Same type of thing. Another unit most people are pretty familiar with is density. Density's formula is mass divided by volume. So in this type of scenario, I'm taking mass and the concept of length to give me another unit, which is density. So we have the fundamental SI units, which are these base SI units that are measured in a standalone form. And then we have any derived unit, which is using a combination of one or more of these units. We're going to be using the metric system a lot in this class. The metric system is a decimal system of measurements with a basic unit for each type of measurement. It's based off of powers of 10, so it makes it really nice to manipulate our numbers. These are the metric prefixes that you will be responsible for in this class. Everything from tera down to nano. So when we look at tera, that's 10 to the 12th power. When we look at giga, that's 10 to the 9th. Mega, 10 to the 6th. Kilo, 10 to the 3rd. Hecto, 10 to the 2nd. Deca, 10 to the 1st. The base unit, deci, centi, milli, micro. That's the Greek symbol mu right there. And then nano for our final symbols that we need to know. So you need to memorize these prefixes that we have. Sorry, this is right here, should be a centi, and that should be a dA for its symbol. So again, as you are trying to memorize these symbols, you can use your King Henry died by drinking chocolate milk thing for the middle section of that, but we go a little bit more expanded in this. Now I can give away my age just a little bit here. I can tell you that I remember the very first computer that I bought when I went to college. Walked into a Best Buy and was talking to the salesman, and he was bragging about the size of the hard drive that he had for this top of the line computer that he was trying to sell me. And I'll never forget, on the thing it said the hard drive had a size of 14.4 megabytes. Now just so you can kind of get a frame of reference for that, probably an individual song that you have loaded on your phone has more megabytes in it than the original hard drive size that I had for my computer. So funny little story with that. Now we're going to talk about doing some conversions between different metric units, and I'm going to give you guys just an alternative method to kind of start off this type of process here. So as we start here, I'm going to rewrite, and I'm going to put some different lines up here. So as we begin to look at our little metric chart up here, I just kind of inverted a little bit to the side. And so what we can do is all of these little dashed lines are representing where the number is not changing its name. So if you think about here with the base unit, that could be your meters, your liters, your grams, your time, so it'd be your seconds, moles, whatever it happens to be. As I go to the left, the deca, that would be 10. The hecto would be 100. Kilo would be 1,000. And then the next line over, by adding an extra 0, I'd now have 10,000, but the thousands part's not changing. The next one I'd have 100,000, and that part's not changing until I get to a million, and then I get to the mega. Then I'd have 10 million, then 100 million, then a billion, then 10 billion, then 100 billion, then a trillion. So as I'm going through those, I'm just making a line to help hold the decimal place, because if you noticed, this was 10 to the 3rd, this was 10 to the 6th, 10 to the 9th, and 10 to the 12th. So I've got the gaps in here for 10 to the 10th, 10 to the 11th before I hit 10 to the 12th power. So that's what these lines are representing. So the easy thing that you can do when you're trying to figure out what the conversion factor would be, and a conversion factor are basically going to be two equivalent measurements that just have a different unit. So when I look at this, what I can do is, since I have 1 for the kilogram, the further to the left I go on the chart, the larger the base unit is when I compare 1 to 1. So what I can then do is just place a 1 on the larger unit prefix, and then I can add zeros until I hit whatever unit I'm trying to solve for. So in this case, 1 kilogram would be the equivalent of 1,000 grams. When I would do the 1 meter equaling 1 nanometer, again, my meter would be here at the base, my nanometer all the way down here at the bottom. So I have a 1 here, 0, 0, 0, 0, 0, 0, 0, 0, 0. So in that case, I'd have 9 zeros, or 8 zeros there, yeah, no, 9 zeros, and I would have 1 times 10 to the 9th nanometers. When I look at 1 centimeter, now in this case, if I place the 1 here, now I got to go back to the base. So I'd be moving the decimal point over until I'd hit the base. So 1 centimeter would then equal 0.01 meters. To go over to the deci, that would be the point that would be there. And then to move it over to meters, I have one more spot, so then I'd add the 0 in to its place for that. When I look at the next example, 1 liter equals blank milliliters. So again, I'm starting here at the base with the liter. 1, 2, 3 zeros that I'm adding on. So I'd have 1,000 for the milliliters. For 1 gram equals my micrograms, I have to go to here. So I have 1, 2, 3, 4, 5, 6 different decimal places. So I'd have 1 million, or 10 to the 6th micrograms. For 1 megaton equals a ton. Again, a megaton is 10 to the 6th power. So I would have 1 times 10 to the 6th tons in that answer. Oh, I don't need to worry about that one. We didn't go to femto. So cross that one off. And then finally, we have 1 meter equals blank HM. So in this case, again, starting with my 1 meter here, I'm having to move to the left, so I know that my hectometers will be larger than my meters. So now I'm moving the decimal point over 1, 2 spots. So I'm going to add the 0 in there. So I'd have 0.01 for my hectometers. So this is just kind of an easy way to help you figure out your conversion factors. And then we can start doing actual calculations, changing them between the different metric units. Okay. So in our next example, we're going to start to look at metric-to-metric conversions using a process that we call dimensional analysis. You may also call it factor label method. Is another way to do it. So if you notice in this example 1, it says that the Space Needle is 184.41 meters tall. It first wants us to convert this into units of kilometers. So based off of our last slide, I know that my conversion between meters and kilometers, for every 1 kilometer, there would be 1,000 meters. So now when we're setting up our conversion factor, what we're trying to do is get our initial unit to cancel by placing that part of the conversion in the denominator, and then whatever we're trying to solve for would be in the numerator. So when I look at an example like this, my first thing that I would do is I would write out 184.41 meters. Notice here I have meters in the numerator, so I can now place 1,000 meters into the denominator, and I would have 1 kilometer in the numerator. And now my meters would cancel, leave me with kilometers, so all I have to do is divide. So I'd have 0.18441 kilometers. And now for the same type of process, I'm going to convert this to units of centimeters. So for this problem, 1 meter is the equivalent of 100 centimeters. So I take the 184.41 meters, and I'll take 1 meter into the denominator. That way my meters will cancel. The equivalent again is 100 centimeters. And now I just need to multiply these two numbers together. So I'd have 18,441 for my number of centimeters. So now in example number 2, it says human hair can vary from about 17 to 181 micrometers. Again, that's the Greek symbol mu, or it's also called microns. So it's asking for what this range would be in millimeters. So for my conversion factor, I know that 1 millimeter is going to be the equivalent of 1,000 microns or micrometers. So when I set up my conversion factor here, I know that I'm going to have somewhere between 17 and 181. So I'm going to take the 17 micrometers, and I would now convert that into millimeters. So that would be 17 divided by 1,000. So I'd have 0.017 for my millimeters. And then I'm going to do the same thing for the 181. So 181 micrometers, 1,000 micrometers is the equivalent of 1 millimeter. So that would be 0.181 millimeters. So my range would be between 0.17 and 0.181 millimeters. We're now going to discuss our English to metric conversions. The English system is the measurement system that we have in the United States, so it's going to be using feet and inches and miles instead of centimeters and meters and kilometers. So scientific measurements are almost exclusively done using the metric system, but most Americans are familiar with the English system. Your conversions between the two systems are often very necessary. So we have those conversion factors that we would use for length, mass, and volume to help us with some of these conversions. So when we look at this in terms of the length, we would have for the English system the inch. For the metric system, we would have a centimeter. So our English to metric conversion would be 1 inch equals 2.54 centimeters, and that is an exact measurement. Now, when we do this, same type of principle is involved. I could have two conversions depending on what I need to have cancel off. I could have 1 inch in the numerator, 2.54 centimeters in the denominator, or I could have 2.54 centimeters in the numerator and 1 inch in the denominator. Which one we choose is based off of what our starting information is given to us in. If we're starting with inches and we're trying to convert to centimeters, then I want to use this conversion on the right. If I'm starting with centimeters and going to inches, then I'd want to use the conversion on the left. In terms of mass, the English unit is a pound, the metric unit is a gram. There are approximately 453.6 grams in 1 pound. And then finally, for volume, the English unit is a quart, the metric unit is a milliliter, and 1 quart is equal to approximately 946 milliliters or 0.946 liters. So now let's look at a few example problems. The speed of sound in dry air is about 343 meters per second. Express this speed in miles per hour. So when I look at this, here's one key thing that we need to watch out for. Notice I have this per. That means that I have two units now, meters going into miles and seconds being converted into hours. But because of the per, that tells me that the time component is in the denominator. So when I set this up, I want to have 343 meters, and then I can have 1 second in the denominator. So we're going to convert each of these different units into the new unit, and it doesn't matter which one we start with. So I'm just going to start, since I had the miles and the 1.61 kilometers, I'm going to go ahead and start with that. So I have kilometers here, you'll notice, and I have meters. So the first thing I need to do is get my meters into kilometers. So for every 1,000 meters, I know that is the equivalent of 1 kilometer, so those would cancel. And now here I have my kilometers and miles. So I could then put 1.61 kilometers and 1 mile in the numerator. That way my kilometers cancel and I have my unit desired in the numerator, which is the mile. And now I need to convert from seconds into hours. So for this, you could say 3,600 seconds equals 1 hour, but just so we can kind of do it in a more traditional fashion here, we know that for every 60 seconds, that is the equivalent of 1 minute. So that way my seconds would cancel. And now from there I need to get minutes into hours. And so for every 60 minutes, I would have 1 hour. So I could take 60 and multiply it by 60 again and have that 3,600 for my seconds in an hour. But we can just show it out where we're converting from seconds to minutes and then minutes to hours. So you'll notice now I have the hours in the denominator. So at this point, all I have to do is take my numbers and multiply them together and divide. Now, just a technique that I would recommend for you guys as you are trying to solve these problems here. And we have a final answer of 767 miles per hour. So I would just simply, a lot of people like to take all the numbers and multiply them across the top and then take all the numbers, multiply them across the bottom and divide. You can sometimes just get into trouble with how your calculator is interpreting your work, and in your mind it makes sense, but to the calculator it's something different. So what I would recommend is I would take 343, divide it by 1,000, then divide it again by 1.61, then multiply it by 60 and multiply it by 60 to come up with your answer for this. That way your calculator is not going to be thinking that you want to take your answer, divide it by 1,000, and then multiply that answer by 1.61. You can do that if you want. Just make sure that when you're putting it into your calculator, you use parentheses to represent your bottom two numbers. Okay, so in our second example, we have a opening sequence of Raiders of the Lost Ark. Indiana Jones steals a gold statue by replacing it with a bag of sand. If the statue has a volume of about 1.5 liters and gold has a density of 19.3 grams per cubic centimeter, how much does the statue weigh in pounds? So we have a couple of different conversion factors that we need to do here. This cubic centimeter, that is a volume measurement, and 1 cubic centimeter is the equivalent of 1 milliliter. So if I have a volume of 1.5 liters, then that would tell me that I would have 1,500 milliliters. So I'm going to start with this, and I'm going to use the density as a conversion factor. So I'm going to start with the 1.5 liters. So I could then say for every 1 liter, there are 1,000 milliliters. And then for every 1 milliliter, that is the equivalent of 1 cubic centimeter. Now I've got that cubic centimeters here that I need to be able to use my density. So now, notice here again that slash or the per sign, so I could write that a little bit differently as a gram over cubic centimeter. So I know that for every 19.3 grams, there is 1 cubic centimeter. That now gets my cubic centimeters to cancel, and now I have grams. Now I need to convert that into pounds, and off of our previous slide, we know that 453.6 grams approximately is the equivalent of 1 pound. So now I can go ahead and multiply and divide. So I'm going to take 1.5, multiply it by 1,000. I'm then going to multiply that times 19.3, and then I'm going to divide it by 453.6, and we end up with 63.8 pounds. With significant figures, we want to look at the numbers that are given to us. Since I have 1.5 liters, that has only 2 significant figures. The 19.3, that has 3. So I'm going to round my answer to only 2 significant figures, and we would have 64 pounds. Okay, so this wraps up our work with dimensional analysis and measurements. There should be a practice sheet on the website for you guys to work through, so please take a moment to go and start working some practice problems. This will wrap up the end of this first presentation. We'll get into the mole concept in our next recording. Have a great day.